All right, so I think we can begin our session. Our first speaker is Alice Bonino from University of Birmingham, and she will be telling us about unveiling eccentricity in the binary black hole mergers. Off to you, Alice.
Yes. Okay. Yes. I am Alice, and I work at the University of Birmingham, and my collaborators are Patricia Schmidt and Geraint Pratten. And I'm going to talk about measuring eccentricity in binary black hole mergers. So, okay. So, first of all, why do we study eccentricity? What is the reason to do this? So eccentricity turned out to be very important to, in particular, to determine formation channel of binary black holes. And in particular, eccentricity seems to be a strong signature of dynamical formation channels. There are also other examples where eccentricity is important that are, for example, extreme mass ratio in spirals or supermassive black hole mergers, or also isolated systems that are perturbed by a third body or n-body. Eccentricity introduces modulations in the phase and in the amplitude of the waveform. So what we want to do is to see how the waveform look like and try to measure eccentricity from the waveform. So in order to measure eccentricity, we need to define eccentricity. So the first definition comes from Newtonian mechanics, and it was given by Mora and Twill in 2002. And this definition it depends on the dynamical quantities. So in particular on the frequency of the orbit. So we have to, sorry, I just closed the window because there is a bit of noise. Okay, sorry for that. The first definition comes from Newtonian mechanics. So from the frequency of the orbit, we calculate the frequency at a pastron and periastron, and then using this estimator, we calculate the eccentricity. The problem of this estimator is that it's not gauge invariant because it depends on the coordinates of the system. So another estimator was introduced that uses the waveform frequency instead of the orbital frequency by Ramos Juarez in 2020. But this estimator turned out to be not to have the correct Newtonian limit. So another estimator was introduced in 2022. And this estimator is now the one commonly accepted by the community. And we know that for this estimator, we still need to calculate the previous estimator. So we still need to look at the frequency at the pastron and periastron of the gravitational wave. And this estimator has the correct Newtonian limit. So what we have done in this work, so we want to define a procedure to calculate the eccentricity from numerical relativity simulations, in particular from simulations that are also relatively short. And this is useful, first of all, to learn something about eccentricity, but also to improve analytical models that can be compared and calibrated to NR and build hybrid eccentric waveform models. But to do this, there are some challenges. In particular, the numerical simulations are very noisy. In particular, at the beginning of the simulation, after Zhang radiation, this noise propagates. And waveform extraction introduces errors, and also there are difficulties in establishing the validity of the estimator, in particular to establish the region of validity of the estimator, because the estimator at some point, when we approach merger, breaks down. So we have to establish where we can use the estimator and also exactly which quantity we have to use. So the idea is to apply this estimator to the data. For this, I chose an example that is a simulation that has mass ratio 1 and an initial eccentricity guess of 0.1 and a line spin of magnitude 0.5. And what we want to do is to find the peaks of the frequency. In order to do that, we use the Neumann-Peron scalar psi4 and extrapolated at infinity, and also the waveforms extrapolated at infinity. To extrapolate the waveform, to transform from psi4 to the waveform, we use a method that is called finite fixed integration. And so for this method, we need a cutoff frequency. So I try to extrapolate the wave from a different cutoff frequency and see what happens. As you can see already from this plot, the first peak has a different position depending on this cutoff frequency. So basically, we apply the estimator to the frequency of the waveform, or the frequency of psi4. So we find the peaks, the maximum and the minima, and then we interpolate the maxima and the minima, and we also define a mean frequency. That is the yellow curve in the plot. And finally, we defined the eccentricity as a function of the mean frequency. What we see is that the eccentricity estimated using psi4 is larger than the eccentricity estimated using the waveform. And also we can note that the eccentricity estimated using the waveform, so when I use different omega cutoffs for the FFI, I obtain curves that diverge. So this is still under study, but maybe this might suggest that there is a region where I want to estimate the eccentricity, that is maybe where the curves converge. And so I was saying that we find that the eccentricity estimated using psi4 and H are not the same, but this ratio is a known ratio from post-Newtonian theory. And what we found is that we actually find agreement with this ratio. And this is quite nice to see. This ratio is the gray curve in the plot, and the blue curve is the difference between the eccentricity estimated using psi4 and the eccentricity estimated using H22, using as a cutoff frequency 0.03, that is the frequency at the first peak of the frequency of psi4 divided by 2. So given that we saw the frequency varies a lot depending on my cutoff frequency, and this is the plot you can see up on the left. Then what I tried to do is now to estimate this eccentricity, I was using five maxima and 5 minima. I didn't account for the last peak. Now I tried to take off the first peak. So on the right, this is what I saw taking off the first peak. So when I don't account for the first peak, this is the plot on the up on the left, on the right. I see that when I estimate the eccentricity using different frequency cutoff, the curve converge, so they look very similar. So this is still preliminary, but because I have to see what happens for different simulations. But this might suggest that we shouldn't account for the first peak. because it's too noisy. And the last plot on the right, on the bottom, shows also what happens if I try different combinations. So I try to account for all the peaks, or not for the first peak, but yes for the last peak, or not for the last peak, not for the last peak, but yes for the first peak, etc. And I find some difference. So this is just to say that we need to investigate and be careful about how many peaks we account when we have short simulations. Something that we also we need to take into account, that was already pointed out in literature, is the definition of mean frequency. In particular, mean frequency and average frequency are not the same. So when we go to later times, so approaching merger, these two curves diverge. So are the red curve and the yellow curve in the left plot. And on the right plot, you can see the evolution of the eccentricity. The two curves diverge also for larger eccentricities, larger frequencies, sorry.
Alicia, you have 3 minutes.
Okay, perfect. So what I've then tried to do was, well, I have a method to estimate eccentricity. So I estimated the eccentricity at the beginning of the simulation. So I have my initial conditions. So I have an initial eccentricity and an initial frequency. And I try to initialize a waveform model. In this case, I use Psi4, but still this is preliminary. I want to try the same method for different from waveform that uses different frequency cutoff as well. But what I see now is that if I don't account for the last peak, the last maximum and minima, I see that this is my plot, the up panel. So I see that there is a good agreement. TOB agrees well with numerical relativity, while if I don't, if I account for all the peaks, I see more disagreement. Yeah, and again, I plot the eccentricity evolution as a function of the mean frequency for numerical relativity simulation and for TOB RSMS. Yes, so in conclusion, we have noticed that we need extra care when we measure eccentricity from short numerical relativity simulations. We have verified that the eccentricity calculated from the scalar Psi4 and from H22 are not the same, but are related through a post-Newtonian relation. And we show that the eccentricity measurement depends strongly on the number of peaks in the gravitational wave frequency. In particular, we saw that the position of the first peak is very sensitive to the extrapolation procedure. And this might indicate that we have to not to account for that peak, but we still need a minimum of peaks for a reliable estimation. So if we still need at least 2 peaks, but if we want to discharge the first peak, we need, of course, 3 peaks at least. We also saw that the estimators break down close to merger, and so we have to be careful about where we cut our eccentricity estimation, and if we need to include this peak or not. We also need to be careful about the definition of mean or average frequency. In particular, when we compare, for example, to waveform models, we need to be consistent to use the same definition. And we, at the end, we compared TOB RSMS Dali waveforms generated using different initial conditions, and we find different agreement. In this particular case, we found that if we don't account for the last peak, we see more agreement. Thank you very much, and I'm happy to hear your questions.
Thank you very much, Alicia, for keeping the time and such a nice short talk. Any questions for her? Okay, I don't see any questions so far. I just have one question. So the definition and the measurement procedure which you spelled out. So this is valid for eccentricity all the way up to high eccentricities?
Yes, I didn't try. I just try eccentricity up to 0.2, but in theory, yes.
Okay, and does that depend on the spins of the binaries? I mean,
no. I tried this method also with this is a line spin. I only have line spin or non-spin in binaries, but this shouldn't depend on this.
Okay, thanks a lot. Let me see if you have any other questions. All right. I don't see any questions so far. So I request participants, if you have questions, you can directly reach to Alice. I'm sure, I think she'll be happy to take more questions from you subsequently. Thanks a lot, Alice, for this talk. Yeah. Goodbye. Yeah.
Bye.
Okay, so let's move on. So our next speaker is Sebastian Khan from Cardiff University, and he'll be talking about accounting for systematic uncertainty advancements in waveform modeling. Sebastian, can you?
Hello.
Hello. Hi. Yeah.
Thank you very much. So good morning, everyone. My name is Sebastian Khan, and I'm going to talk about probabilistic waveform models. So the motivation for this work is that we would like to avoid biased inference that arises from model uncertainty. So to illustrate this, suppose you have some training data, which maybe they represent waveform models, waveforms, and you fit a model to this data, and then you have a new observation, and you want to ask yourself, should you trust your model here? Now, typical models, they don't have any form of uncertainty estimation built into them, so you have no way of knowing what this gap is between your model and the observation is, unless you actually go and perform, say, another numerical relativity simulation there, for example. So in this work, what we want to do is we want to be able to equip our waveform models with some form of uncertainty estimates and guard against biased parameter estimation. So yeah, in this work, we are presenting an extension to the phenomenological modeling workflow, which we're calling probabilistic phenomenological models. So these are probability distributions of the waveform strain H. And as such, you can generate not only the mean waveform, which would be your traditional best fit waveform from typical models, but you can also sample from this distribution to generate waveform samples, which hopefully should be quite realistic realizations of potential waveforms. I'll describe the method in this talk, which we use a semi-parametric approach, which just means some parts of the model are parametric, some parts are non-parametric. And this is really just a proof of concept work. So we only really focus on quite short simulations, 2-2 mode only, non-spinning binary black hole simulations from numerical relativity. And our data set consists of 25 unique mass ratios from mass ratio 1 up to mass ratio 32. And 10 of these mass ratios have more than one simulation, which we sample from 4 different codes, which forms a basis for our sort of naive error estimation. And these error estimates directly feed into our non-parametric fits. So our sort of simplified workflow looks like this, where we have our numerical relativity data set, and we first perform some sort of strain alignment. For this case, as it's just 2-2 mode only waveforms, we can simply do a time and phase shift basically to put them into the same reference frame. And then for each strain, we decompose, as we typically do, into an amplitude and frequency representation. And then we split the waveform into 3 regions in interval merging ring down. And then for each of these combinations, we perform the following. We first, of course, perform our parametric fits, and in parallel, we can estimate the uncertainty in those waveform models as well, in those NR simulations. Both of these feed into our non-parametric fits, and then ultimately they go on to form the final model. So the first thing we need to do is estimate the error in numerical relativity simulations. Ideally, we would use, if available, a full convergence series for each NR simulation to estimate this NR error budget, but this is difficult to do for a number of reasons. NR simulations are very computationally expensive, so simulations simply just don't exist for a complete convergence series everywhere. And there's also subtleties between different numerical relativity codes, which make it difficult to form comparisons. So we sort of leave that difficulty for future work and take a very simple pragmatic approach where we simply align waveforms like I was mentioning and just compute residuals between them. And the big assumption here, which is the big negative, is that it assumes that all simulations are equally accurate, which is definitely not the case, and certainly not here, because I explicitly use simulations of lower resolution to have more variety in the training sets. So next few slides, I'm going to walk you through sort of what the data looks like. So here I've taken the mass ratio 4 simulations in this data set. There are 7 of them from 4 different codes. This is the strain as a function of time after we've performed time and phase shift to try and optimally align them all together. We'll now convert them to an amplitude representation, and we'll zoom in around the peak so we can really see the variation or variability in these simulations. So from that bird's eye view, they all seem to agree really, really well. But when you take a very detailed view, you can see there's disagreement between them, which again, for this data set is not so surprising because, like I said, some of the simulations are at much lower resolutions than others. But in theory, we want to be able to capture a variety of morphologies with a model. So you can see there's amplitude differences, there's also differences in the peak of the waveform as well. So we want to be able to capture this uncertainty in a model. Normally, you would just pick one of these simulations when you're modeling and assume that was the correct one or the most accurate one and just try and model that. So now we need some modeling methodology which is a bit more flexible. So like I said, this is an extension of the phenomenological workflow. So we start with phenomenological fits, and this is the parametric portion of the model. And the reason why we extend phenomenological models is because we can make use of all the excellent work that everyone has done over the past years. So for example, in a parametric model, we propose some ansatz, like this one on the top right, proposed by Hector, or similar to the one proposed by Hector, which is very powerful and flexible ansatz to fit the amplitude model, the amplitude data, which I show here. And we don't use a least squares regression approach, which is what you would normally do to determine or to constrain these alpha coefficients up here. Instead, we use a co-location point method, which I think Sasha first introduced back in 2016, which is a really nice method in certain situations. So here, the co-location point method changes the focus of the model from these alpha coefficients to a new set of coefficients, which are values of the waveform at particular points. So here we have 4 co-location points, as well as a derivative constraint, which are 5 degrees of freedom, as we have equivalently here. And one of the main benefits of the co-location point model is its interpretability. It's very interpretable because the coefficients now, or the errors in the coefficients, are now directly identifiable with errors in the amplitude or frequency or whatever you're trying to model at those co-location points, which also plays very well with what we're going to do next and how to introduce variation into our model, basically. So on this slide, I've taken one of those NR simulations. Again, we zoomed in around the peak of the amplitude. And for the NR uncertainty, which is this orange band, it's just the minimum maximum of all those 7 mass ratio 4 simulations. And we're going to fit this ansatz in the top right to this data like this using co-location point methods, where we have one co-location point highlighted here at the peak. And because this is the coefficient of our model, we can manipulate it. In particular, we can perturb it and generate basically new functions, which hopefully will fit the data in a realistic way. And the amplitude of this perturbation, of course, we'll learn from the data as given by this uncertainty region. So once you have your collection of coefficients for your model, this is a discrete set of points at your training points. You need to convert this into a functional model. And here, this is the non-parametric part of the method, and it's used for the parameter space fits. And here we use a Gaussian process because it's very flexible. It's very easy to get an accurate model for your data. And we can easily incorporate the NR estimate of the error at the training points. And also with a suitable choice of kernel, we can introduce this distance awareness property, which all that means is that when you move away from your training set, you want your uncertainty to grow, like it does here above after these blue points. So onto the test results. The main test results I'll present are in the form of a mismatch error, which is on the y-axis. So the smaller it is, the more accurate the model is as a function of the mass ratio. So in blue and orange are the train and test set results for when you take your probabilistic model, you compute the mean waveform, and you compare that to those NR simulations, and you will get these values for the mismatch. The values are around about 10 to minus 3 or so, indicating that the model is indeed fairly accurate, at least up until mass ratio 18. Now, when you try this model, and compare it against the mass ratio 32 waveform, the waveform is deep into extrapolation region and is not accurate here, indicated by this large mismatch. And normally with standard models, this is where your analysis would stop. But we have a probabilistic model, which means that we can go one step further and we can estimate the model's own uncertainty. And we can do that using something which we call the predicted mismatch distribution, which is all of these green curves here. So predicted mismatch distribution is just the mismatch between the mean prediction of your probabilistic model, which is H bar, and a number of samples which you draw from your probabilistic model as well. So for each mass ratio, you're now going to get a range of mismatches. And in dark green, this is the median value of this distribution, which you can see traces out fairly nicely, most of the time anyway, where you have training data, so where your fit is constrained by observations. And then in the regions between and in the regions where you extrapolate, the uncertainty grows as you would expect and as you would like it to behave. So this is really good because now we can say, even without having this mass ratio 32 observation, we can already make a prediction for how accurate we think the model is going to be. And the model believes it's going to be inaccurate, and it is inaccurate, which is good. It can tell you when it doesn't know something. On the left now is the same plot as before, but on the right, I'm going to highlight a few of the test waveforms. So this is the mass ratio 4 and the mass ratio 8 case. In black dashed lines is the numerical relativity simulation, or one of them I picked. And in blue, there's actually the mean waveform plotted here and 100 samples from the model as well. And the reason why they look quite boring is because the mean waveform has an accuracy of better than 10 to minus 3 here, and the predicted uncertainty has also an accuracy of just above 10 to minus 3 or so. But when we go to mass ratio 15, the predicted error touches 10 to minus 2. And so we start to see some visible differences, although it's fairly minor here, of around about minus 100 M, which is where we transition from an in-spiral region to the merger region in the model. And then when we get to mass ratio 32, the model is extrapolating well beyond where it's trained. And the way it expresses that is by producing a large variety of waveforms, but each of which mostly resembles a waveform, hopefully. And my final slide that I would like to discuss is that even though that you have a probabilistic model, you don't really have a guarantee that the uncertainty width, or the width of the uncertainty that it predicts is indeed accurate at all. So you need to make sure that your probabilistic model has a calibrated uncertainty, or at least measure it, what the calibration is. So it turned out Doctor in 2017, when he was working on a Gaussian process model, wrote down something very similar, which is what we call the calibration score. And it's just the ratio of the true error and over the estimated error. So the true error is the mismatch between the best fit waveform, which is the mean prediction from the probabilistic model, and the numerical activity, and the estimated error is the predicted mismatch distribution from the previous slide. So the calibration score is a probability distribution P of C. And when this score is 1, you have a perfectly calibrated model. You can accurately predict what the mismatch error will be purely from your model. If it's greater than 1, then you're overconfident. And if it's less than 1, then you're underconfident. And I have the training and test results here in blue and orange again, respectively. And we can see that the model is about 10 times is accurate to with a value of about 10 in terms of being overconfident or underconfident.
Sebastian, you had 3 minutes.
Thank you very much. And we sort of have to ask ourselves what is the steps forward in order to improve this. Well, the first thing is, will adding more data simply improve the calibration score here? Maybe that's all we need to do. The second point is that perhaps there's some systematic bias present in this data set. As I mentioned earlier, we assumed that all the NR simulations were equally accurate, and that they definitely weren't, because I was on purpose including some simulations which have lower resolution. So this might be the cause of some of these sort of outliers here at low mass ratio. They're sort of systematically overconfident, and at higher mass ratios, they're sort of systematically underconfident. It's also that we have fewer NR simulations from different codes. So for the mass ratio 7 and the 15, I think these only come from one particular code for example. But if this is not the case, and this method doesn't generally produce calibrated uncertainty estimates as is, then we may need to invest in developing a method which can calibrate the uncertainty estimate, perhaps either in a post hoc manner. So my conclusion slide is here. So we've developed an extension to the phenomenological workflow to build probabilistic phenomenological models. And the two key outcomes of this work, in my opinion, are that one, we really need a better understanding of the NR error budget if we want to be able to produce or to build accurate uncertainty models. So for example, if every NR simulation came with a error budget time series, that would be fantastic. How realistic that is, I'm not sure, though, because it is very computationally expensive. And the second point is we may need to develop a further method to actually calibrate the uncertainty estimate that comes from this model. However, if we have those 2 points covered, then that would be the time to go on and extend to more complete descriptions of mergers, for example, higher multiples and precession, where arguably these PPM type models would be most effective here, because I just realized I'm out of time, because yeah, they're more difficult to model, and ultimately, hopefully we can use these kind of probabilistic models to marginalize over waveform uncertainty and parameter estimation. Thank you very much.
Thank you very much, Sebastian. Questions? Yes, Shrobana Ghosh.
Hi, thank you. Sebastian, thank you very much for that talk. It was very interesting. I have a question about the alignment for the NR simulations that you mentioned. So maybe you mentioned this and I missed it. For the aligning, did you just align the phase, or did you get them to have the same value at a particular frequency, or the peak of the waveforms?
Thanks, Shrobana. It's a great question. So the way the alignment works is a little bit strange, because you have multiple NR simulations at a single mass ratio. So what we do is a time and phase shift, basically optimally align them using an overlap function over, say, the first 800 M of the signal. So not necessarily the whole waveform. But then within each mass ratio, we then, so they're aligned in phase, but because they can peak at different times, they're not all aligned at t equals 0. So basically they're aligned at the beginning. Okay.
So do you, I don't know if it's meaningful to align the peak, and if you do that, do you think the results would drastically be different or not much?
Yeah, that's a good question. Before, people used to quote NR error estimates, like 2 error estimates, one where they would align near the beginning of the waveform and one when they were lying around the peak of the waveform, because maybe they weren't sure, at what point, like in the previous talk, whether the first part of the waveform maybe was contaminated a bit with some error, which they weren't sure about, and then maybe you get a cleaner estimate towards the peak. So I think the results could change, but I sort of preferred to assume that everything could be aligned at the beginning, and then any drift was a result of NR error as it was evolving.
Okay, all right, thank you.
Sebastian, there is one more question in the chat. So I'll just read it out for you. It's by David Keatle. He says that for P marginalization, do you think the direct sampling from the uncertainty model will be feasible computationally, or better to fit envelopes?
That's a great question, David. I think it depends on the how well the code is optimized. I think there are particular codes out there, for example, to do very efficient Gaussian process like sampling, and potentially even in parallel. So I haven't done any speed tests here because that's not the purpose of this work, but I think it's feasible. And you will have to resort to, fitting the envelopes.
All right. Thanks a lot, Sebastian, for this nice talk. And thanks, everybody. Let's move on to the next speaker. The next speaker is Xian Chen. Hello, Xian.
Sorry, he cannot be here because he's on a trip. So I, as a co-author of the paper, I will be talking about the paper. I am Xiaoyue Zhang.
Okay, welcome. So she will be talking about the appearance of LIGO Virgo KAGRA sources in the AGN accretion disk. And I guess you are also from Peking University, China, right?
Yes.
Okay, yeah, you can start sharing your screen. I will remind you after 12 minutes.
Okay, thank you. Hello, everyone. It's an honor here to talk about our work, the appearance of LIGO and Virgo and KAGRA sources in AGN disks. Until the third observing run, LIGO and Virgo have detected up to 90 binary merger sources events, and 83 of them are identified as binary black hole merger events. And one feature of these black holes detected by LIGO and Virgo is that their mass distribution is significantly higher than the black holes previously detected by X-ray. And another problem about the mass of these black holes is that we later saw that there are some massive events, and the primary mass of the black hole before merger is already around 100 solar masses. That is already in the current stability mass gap, and this is hard to explain it in the traditional stellar evolution theory. People have suggested several solutions, possible solutions to solve this problem. Well, my supervisor, Xian, and his collaborators suggested in 2019 that this mass problem might be due to the mass redshift degeneracy. So it's a problem caused by the measurement, because we know that the observed chirp mass seen by the observer is actually a real chirp mass timed by a redshift 1 plus z. So if the source is isolated, then as long as the observer gets the right cosmological redshift and remove it, then the observer gets the right chirp mass. But suppose the source is in an astrophysical environment, for example, it is very close to a supermassive black hole, then because the source will have a large velocity and also in a deep gravitational field, then actually the signal will go through both a large Doppler effect and a gravitational redshift. And because the observer will not consider these two effects, then the observer can overestimate the the chirp mass of the source. And also they argued that because the distance measured by the observer is also proportional to the observed chirp mass, then it will also be carrying these two additional terms and can be larger than the real luminosity distance of the source. Xian and another student in our group, Peng Peng, suggested in 2021 that in the slim disks, the black holes can migrate into the very inner region of the AGN disk, very close to the supermassive black hole, as close as to a couple of Schwarzschild radii from the supermassive black hole. And here, these two effects will be quite significant. They estimated the event rate and showed that the event rate of this kind of sources can be up to 1% of the LIGO and Virgo events. So this kind of effect might not be negligible. In this previous work in 2019, people used Kepler velocity to estimate the Doppler shift and used the Schwarzschild black hole as the central supermassive black hole to estimate the gravitational redshift. But this may not be very appropriate because the source is already very close to the supermassive black hole. And another problem is that actually when the ray is traveling so close to the supermassive black hole, then the deflection, the lensing effect will play an important role. And here, as we can see, because we have an amplitude in the formula here, then it will influence the measurement of the distance. But this was also not considered in the previous work. So in this recent work, we are putting a cursed supermassive black hole in the center, and we put our binary black hole source on the equatorial plane orbiting the supermassive black hole. Then we will be considering both the redshift effect caused near the supermassive black hole and the lensing magnification effect. We will be dealing with the calculations numerically, and because we are considering the LIGO and Virgo events, then these events will meet the geometrical optics limit. So we'll be simply considering the motion of the geodesics. First, let us reconsider the influence of these effects on mass and distance with both redshift and magnification in our mind. We have introduced that the distance is proportional to the observed mass and inversely proportional to the amplitude. Then because we here have the magnification as an additional effect, then as a result, in the ratio of the observed distance versus the real luminosity distance, we see for the first part, the term caused by the Doppler effect and the gravitational redshift, and the second part caused by the lensing magnification effect. And then we go back and reconsider the problem of the inferred chirp mass by the observer. Actually, we notice here that not only the Doppler effect and the gravitational redshift that we talked about will influence the measurement, but also because we here our observer will have a wrong estimation of the luminosity distance, then actually the cosmological redshift of the source will also be estimated wrongly. Then there will be this additional third term coming here, and this is because the observer is not getting the correct cosmological redshift. So overall, we will be considering the redshift effects and the magnification effect, and they will be influencing the measurement of the mass and distance of the source. From the beginning, we look at how we calculate the redshift. Actually, the calculation of redshift is quite easy. It's just the energy seen by the observer of the signal will just be minus p mu u mu. Here, p mu is the momentum of the geodesic, so that is of the signal, and here u mu is the velocity of the observer, and then the redshift seen by the observer will simply be the energy seen by the emitter divided by the energy seen by the observer. Here, because in this form we actually already have both the velocity and the metric, then the form already contains both the Doppler effect and the gravitational redshift. Then for an observer at infinity, the formula will take such a simple form. And because we will be considering observers at large distance, then we will be using this formula to calculate the redshift seen by distant observers. Also, we could also make plots and see how the redshift is distributed along the trajectory and how it is seen by the local observers along the trajectory at finite distances. To do this, we introduce the locally non-rotating observers. And here we show two plots showing how it is distributed on the equatorial plane of the supermassive black hole. We have a black star here, and this is the location of the source. Then we see as the rays come out of the source, the redshift and blueshift rays are distributed symmetrically because they are only experiencing Doppler effect here. But as the rays travel farther from the supermassive black hole, we can see that because of the gravitational redshift, then the rays become more redshifted. And as a result, on the right, we can see as the rays travel to distant observers, overall, they tend to be redshifted. And this kind of explains why the effects we consider, they tend to make the observer see redshifted and more massive events than the real sources. And another feature we see here is that on these directions we can see two rays coming to a nearly same direction, but they have very different color, and this means that on this kind of directions, an observer sitting on the direction will see two images, but they will seem to have different apparent redshift, and they will be identified as different events. We have introduced how to calculate the redshift simply. That now let's see how we calculate the magnification. We introduced before that the magnification will influence the measurement of the distance. Here we introduce the frequency, the area intensity law with the changed frequency introduced by Campbell and Metzner, and they actually considered the problem of the deflection of gravitational wave because they wanted to solve the problem why the gravitational wave signal seen by the Weber bar had such a big energy intensity. And we notice here we have a -2 of the frequency nu here in the formula, but the flux here is proportional to the square of the frequency. So as a result, the amplitude is just inversely proportional to the square root of the area that's the rate bundle span. Then we further notice that as the rate bundles travel to larger distances, they are nearly straight and are directed just nearly to the supermassive black hole. So we can change this ratio of the areas into the ratio of the solid angles. And here to calculate the solid angle seen at the emitter, we will use the rest frame of the emitter, and to calculate the solid angle span at the distant observer, we simply need to calculate it relative to the frame of the supermassive black hole. So that is the Boyer-Lindquist coordinate. So in the end, this calculation of magnification is simple. We calculate the trajectories of the rays and then calculate the solid angles numerically and get the results. Now let's see how the magnification is distributed for the observers. Here we first show
You have 3 minutes. Thank you.
Oh,
you have 3
thanks.
minutes. Yeah, thanks.
Thanks. The magnification seen by in the rest frame of the emitter, and on this 0 degree direction will be the direction of the velocity of the source. Here on the right, the white patch is the region where the rays cannot escape to the infinity, but will fall into the supermassive black hole. We see in this plot a very bright yellow ring, and this means that on this ring there is a high magnification. And what in our calculation, we see that what is happening here is that crossing this ring, inside this ring, we see that the rays are overlapping with each other, crossing each other. And outside this ring, it is not happening. And this actually meets the definition of acoustic in optics. So, so this ring, it becomes an envelope, and outside there are no overlapping rays. So we will call this ring an acoustic, and to make things clearer, we will separate the rays outside and inside this acoustic ring to show the distribution of the rays seen by the observers. So here we show the distribution on the sky of the supermassive black hole when the rays will arrive at distant observers, and we see here both on the left and right, near this point, there is a bright yellow small region where the magnification is high, and that is actually where the bright yellow ring we saw before converged to. And this means that this highly magnified region is can hardly be seen by the observer because it makes up a very small region of the sky. And then we see that on the left, the rays from outside the acoustic, they experience a moderate magnification, and on the right, the most rays are experiencing a high demagnification, and we see a similar. We can also look at the redshift seen by the observers, and we see that for the rays outside the acoustic, most rays are highly redshifted, and for the rays from inside the acoustic, most rays experience a moderate redshift. And we need to note here that because the rays coming from these two plots are actually on the same sky map, but we are manually dividing them into two maps. So that means the observers on an direction will see two images that will seem to have very different redshift and very different magnification, and that means the observer will see two images with apparent different mass and distance, and will identify them as different events. Here we show the distribution of the events seen by the observers in the parametric space. Here on the horizontal axis, we show the apparent cosmological redshift of the source, and on the vertical axis we show the chirp mass inferred by the observer, and we see that for the rays that are above the horizon of a LIGO, most rays seem to have a larger seem to have a larger mass and a larger distance than the real case. And we also show that on the right end, we see that for some of the images, the images will seem very far and have a very low mass seen by the observer. And these can be identified as subsolar primordial black holes, although they cannot be seen by a LIGO, but might be detected by future detectors. So these are my conclusions. The gravitational waves emitted around a supermassive black hole will tend to be redshifted and demagnified, and will tend to appear more massive and distant than the true case. Sorry, I forgot it, but the inferred chirp mass can be over 5 times of the true chirp mass. So that means a source with 20 solar masses will be identified as 100 solar masses. And also many observers that can see 2 images, but will not be able to identify them, but see them as different events. And also there are some images that are strongly demagnified, and in the future they might be misidentified as subsolar primordial black holes. Thank you.
Thank you. Thank you very much. And let's see if there are any questions. Okay, so let me ask you a question. Can you sort of suggest, I mean, this would be more relevant in the future detectors, or, I mean, is there something which you can, have you guys thought about regarding, you know, the events which one can detect this effect?
Yes, we are currently working on this problem because our goal is to identify them. So now we are thinking, because the 2 images, they will come from the same sky region, and also because the time scale of the system is less than a day, then if we see 2 events and they're in the future, and they're from the same sky region, and have a similar mass ratio, and also they the time difference of the 2 events will be less than a day, then we might be able to further investigate whether they are coming from the same source. But it's still a problem how we can distinguish these images from different sources. Yeah, it's still a problem of our work.
Okay. Okay, thanks a lot. Thank you very much.
Thanks.
All right, so now we are going to take a break of 10 minutes, and then we will reconvene after 10 minutes for the next set of talks. Thank you very much. All right, let's begin our session. Okay, the next speaker is Eleanor Hamilton.
Yep.
Hello, Eleanor. So Eleanor is from University of Zurich, and she is going to tell us about the complete IMR higher mode model for processing binaries. Eleanor, I think you can share your screen. I will remind you after 12 minutes, start.
Excellent. Thanks very much. Okay, so to date, the LIGO Virgo KAGRA collaboration has detected gravitational waves from 90 compact binary coalescent systems, most of which are binary black hole systems. And we can make measurements of the properties of these binaries, so the masses and the spins of the black holes that make up the binary, using models of the gravitational wave signal as predicted by general relativity. And these measurements are then used in constructing a picture of the astrophysical population of black holes and identifying how they're formed and using them as tests of general relativity in the strong field regime. So it's really important that we have accurate models of these systems. The properties of the black holes leave a very distinct impression on the gravitational wave signal. And some of these are very easy to identify. For example, the total mass of the binary just affects the frequency scaling. So heavier binaries merge at lower frequencies, but some are much harder to unambiguously identify. And one of the effects that's particularly hard to clearly detect is whether the black holes are spinning. In binaries in which the black hole spins are randomly oriented, we call these precessing binaries. And while this has a definite impact on the signal, it's very difficult to actually measure. So during the previous observing run by the LVK, we have started to see evidence for a population of precessing binaries. And in the current ongoing run, we expect to see a larger population of events where we are able to make unambiguous measurements of the degree of precession in the signal. And we therefore want and need highly accurate models of precessing signals that are applicable at all mass ratios in order to analyze these signals. However, it's really quite challenging to model the waveform from precessing signals. In a non-precessing binary, the majority of the power is radiated in the dominant multipole, generally referred to as the 2-2 multipole or the 2-2 mode. But in a precessing binary, the power is spread out between all the other modes. So like you can see here on this slide that all the different, the higher multipoles include, have similar amounts of power to the 2-2 and the 2-2. And we also see oscillations in the amplitude and the phase of the signal. Also, the precession induces asymmetries between the positive and negative M modes, and these are known as mode asymmetries. However, we can track the precession and transform into a frame which precesses along with the binary. And in this frame, the waveform appears non-precessing and does not have oscillations in the phase and the amplitude. And this is what's shown here on this slide, is the same waveform that we saw in the previous slide, but transformed into the co-precessing frame, where now the dominant power is clearly in the majority of the power is clearly in the dominant multipoles, the 2-2 and the 2-2. We have an approximate mapping that this co-precessing waveform is equivalent to an aligned spin binary, but where we make adjustments for the final spin to account for that of the precessing system. The rotation into the co-precessing frame is described by a set of Euler angles, alpha, beta, and gamma, which are referred to as precession angles. And these are shown in the bottom left-hand corner here. Alpha gives the rotation of the optimal emission direction into the XZ plane. Beta gives the rotation into the Z direction, and gamma is given by something called the minimal rotation condition, and just ensures that the co-precessing frame is uniquely defined and artificial phase artifacts are not introduced by the rotation. So from this, we can see that when we model precessing binaries, we want to split it up into two components. The first being a model for the non-precessing gravitational wave modes in the co-precessing frame, and the second being a model for the precession angles, alpha, beta, and gamma. And here I will present the model for NOM-X04A, which is a complete precessing system model. So this is the first complete inspiral-merger-ringdown model where the precession effects are tuned to numerical relativity. And so as a first pass, we consider only single spin systems. And since the two spin systems just introduce small oscillations on top of the underlying simple precessions. We place the spin on the larger black hole and neglect the effect of varying the in-plane spin oscillation orientation. And this reduces the 7-dimensional parameter space made up of the black hole masses and individual component spins to just a 3-dimensional parameter space of mass ratio, dimensionless spin magnitude, and the spin inclination angle. We want to cover the largest possible parameter space with our numerical catalog, which we've produced in order to calibrate our model to these simulations. It therefore was feasible for us to perform the necessary number of simulations up to a mass ratio of 8 and a spin magnitude of 0.8. However, the LBK has already observed a system with a mass ratio of around 10. So we do want to extend this up to higher mass ratios as a matter of some urgency. The catalog comprises of 4 equally spaced values in mass ratio, 5 and spin magnitude, and 5 in spin inclination angles, excluding aligned and anti-aligned systems where we already have a large number of waveforms. We expect that this should be sufficient to capture the dependence of precession on these parameters. So the catalog contains 80 waveforms in total and is now publicly available, all the data from that catalog, if you go to the links in the bottom left-hand corner of this slide. So first, I'm going to talk about the co-precessing model of the dominant multipole. So the dominant multipole model is the part where we have calibrated it to numerical relativity. This is based on the model Phenom-XAS, and essentially we have modified the late inspiral and merger ringdown behavior of the frequency and the merger ringdown behavior of the amplitude by retuning key parameters in the ansatz and calibrating these against the numerical simulations I've discussed on the previous slide. The main changes are a modification in the effective ringdown frequency and the damping times beyond just the simple readjustment of the final mass and spins to correct for the precessing system, which I've already described. And we can see the effect of recalibrating, for example, the phase derivative in the bottom right-hand plot on this slide. The most crucial thing in the retuning is the ringdown frequency. Previous models for precession have employed an aligned spin model for the co-precessing waveform and then just adjusted the ringdown frequency and damping time to allow for the full precessing configuration, using final mass fits from aligned spin binaries and final spins obtained by fitting using the aligned spin binary fits, and then adding in the in-plane spin component, which is assumed not to change through the evolution of the binary. And this approach leads to a discontinuity in the value of the ringdown frequency as we move across the parameter space. And if you take a look at the plot in the top right-hand corner of this slide, this is indicated, for example, from Phenom PV3 in the dotted black line. We have 2 choices of the ringdown frequency, depending on whether the binary orbit is prograde or retrograde with respect to the final spin. So the solid gray line in this plot shows the prograde frequencies, whereas the dashed gray line shows the retrograde frequencies. If we consider a binary orbiting in the XY plane and merging to form a black hole with spin in the Z direction, then if the black holes are orbiting clockwise prior to merger, then the perturbation on the final spin will be on the final black hole will be in one direction, whereas if they're orbiting anti-clockwise, then we get the perturbation in the opposite direction. And this is what corresponds to these 2 different ringdown frequencies known as the prograde and the retrograde frequencies. The discontinuity in this figure is seen for a spin inclination angle of around 120 degrees, where essentially the final black hole spin goes from positive to negative with respect to the orbital direction, and the frequency jumps from 0.08 to 0.05. Around that value. This prediction of the ringdown frequency, however, comes from perturbation theory, which is calculated in a frame in which the final spin is parallel to the Z direction, not the co-precessing frame. And it is the co-precessing frame in which we want the ringdown frequency for modeling purposes. And this rotation into and out of the co-precessing frame shifts the frequency value. And so when we apply the perturbation theory result in the co-precessing frame, we get the wrong result in the J frame. So now we have retuned, showing the calibration points of the circles, the dots on this figure, and the black line through them shows the recalibration. So we can see that we now have a smooth progression of the frequency in the co-precessing frame. And when the rotation is applied in order to get into the J frame in which we have our final model, we will then have the correct ringdown frequency in that frame. Further, this dominant multipole model also includes multipole asymmetry, which has again been calibrated against the NR simulations, and this will be given in much more detail in Shrobana's talk, which is coming up next, where she will present the first phenomenological model of asymmetry. So now moving on to the other key component of our model, which is the precession dynamics. This model consists of two parts. First, where we describe the precession during inspiral, and the second part is a phenomenological model tuned to the numerical catalog, showing the precession angles during merger and ringdown. In the inspiral part, the angles are calculated using post-Newtonian theory, which gives a closed form analytic expression describing the inspiral precession dynamics. And these expressions model two-spin and in-plane spin effects. We can see from the figures on this slide that these expressions model two-spin and in-plane spin effect well during inspiral, but they do not agree with the NR during merger ringdown. And the expression for beta never agrees, even at low frequencies. So instead, we have developed a phenomenological model where the coefficients are tuned to numerical relativity, and this captures the key features of the angles, such as the drop-off in beta, and this induces the mode hierarchy, where this rapid drop in beta means that the turnover of the different multipoles occurs at different frequencies.
Eleanor, you have 3 minutes.
Thank you. So now, having made the dominant multipole model, we now want to extend to higher multipoles. This higher multipole model is not calibrated to numerical relativity. And it is complicated in the frequency domain because in the higher multipoles in the co-precessing frame do not exactly represent those of a non-precessing binary. So instead of using a single rotation for all multipoles, we use a frequency rescaling to define the angles, which takes us from the inertial frame into a frame in which the majority of the power is in the dominant multipole, and the waveform resembles that of an aligned spin binary. During the inspiral, we use the stationary phase approximation to do the rescaling, and during ringdown, we rescale based on the relative ringdown frequencies. And this rescaling is demonstrated in the figure here. The final modification to the extension to higher multipoles is to account for the effect of the rotation on the ringdown frequencies so that we get the correct ringdown frequency in the inertial frame. For this, we use an analytic effective ringdown frequency prescription, which is not unique to phenom models and has also been employed in the latest SEOV NR model. Because these extension to higher multipoles employs these approximations and does not employ numerical calibration, there is room for improvement with this higher multipole part of the model. So here I'm going to show the match results, the comparison between our dominant multipole model and the numerical calibration set that the set of numerical waveforms that was calibrated against. We can see that this dominant multipole model is hugely accurate, although we could still get improvements at high mass ratio and high spin, but we think we will need longer NR waveforms in order to do this. The light green triangles here show a model that was calibrated against just a subset of 40 of these waveforms, and the dark green show calibration against 80. So we're confident, based on the comparison of these results, that this improvement in the model due to calibration does not come from over-tuning. But we do see a definite improvement over, for example, on this slide, SCABNR V5 PHM, which is the latest state-of-the-art precessing higher mode model, but does not include the tuning of the precession effects. Unfortunately, when we do include the higher multipoles, this does degrade the accuracy of our model, although it's still comparable and to some extent an improvement, particularly in the worst cases, against current state-of-the-art models. This is in part due to the necessary approximations and subtleties related to modeling precession in the frequency domain, and in part due to a lack of tuning of the higher multipoles. But also because more multipoles means more structure, and so it's harder to make an accurate model. But we anticipate that calibrating this higher multipole component will result in a clear improvement of the model. So now that we have a sense of the model accuracy, we need to translate this into an actual impact on the data analysis of gravitational wave signals, and that can the model accurately return the properties of the signal. For standard events, we find that the model works well and shows no pathologies and agrees with other recent models, as demonstrated here on this slide for GW 150914. And we also find that this is true for less vanilla events, such as GW 190412, which has a higher mass ratio and a definite non-zero aligned spin. However, we still want to understand how the model performs for precessing systems where the precession effects are detectable, particularly those at higher mass ratios. And the best way to do this is by performing an injection study so that we know the properties of the signals we are analyzing. So we injected the NR surrogate model NR7DQ4 at a known set of parameters and used the advanced LIGO noise curve. And we find that in the parameter space with mass ratios less than around 4, all current models tend to perform relatively well. And the standard aligned spin parameters are always correctly recovered, masses and chi-effective. But not all models are able to correctly capture precession properties in all parts of the parameter space. And so we need to improved models in these cases. Here we have a case where SUVNR V5PHM and Phenom X04A accurately recover the in-plane spin component, but predicting exactly which models reliably recover the properties across the parameter space would require a more in-depth study than we've been able to perform so far. And so the key takeaway from this is that all of our models really do require further improvements. Thank you. I will just leave the conclusions here because I think I'm a bit over time.
Thank you. Thank you for this nice talk. Questions? Okay, while people think about the questions, I have one question. Did you try to apply it on 1905-21 event?
I think we, sorry. I was trying to remember if it was one of the events. I think we may have run on that event, but because that event is quite a short signal and quite a noisy signal, I don't know that we have any particular strong conclusions to take away from those.
Yeah, because that also shows some evidence for precession, right? So I was just curious.
It potentially shows evidence of precession. I would, yes, but not conclusively.
That's right. Yeah. Okay, let's see. All right, I think. All right, thanks a lot. And Eleanor, if there are any questions, please reach out to her. I'm sure she'll be very happy to answer your questions. And once again, thanks for this nice talk. All right, so let's move on. So our next speaker is, so Shrobana Ghosh is going to tell us about first phenomenological model of multiple asymmetry in gravitational wave emission from compact binary coalescence. And she is from AEI Hanover. Off to you, Shrobana.
So I will be presenting the first phenomenological model of mode asymmetries in compact binary coalescence. This work was done in collaboration with Panagiota Kolitsidou and Mark Hannam. So Eleanor already spoke about precession dynamics. What I will talk about is a consequence of having spins in arbitrary direction where the motion is no longer confined within a fixed orbital plane. The main thing that happens is because of the components of misaligned spin, the reflection symmetry in the plus and minus m modes no longer holds. So we cannot just model the 2-2 mode and construct the 2-2 mode from the 2-2 mode itself. And the reason why this is important is because this asymmetry is responsible for the out-of-plane kick that would be experienced by the merger remnant. All of the current waveform models, except for the NR surrogate model, still continue to operate with the reflection symmetry that I mentioned earlier, even for precessing systems. Now, to give you an impression of how noticeable this would be. On the plot, I show the 2,2 and the 2-2 mode from a numerical relativity simulation for the last 10 orbits or so before merger. And as you can see that the 2,2 and the 2-2 mode amplitudes seem to oscillate about a mean value. This is a spin orientation effect. This happens only when you have spins that is misaligned from the orbital angular momentum or the perpendicular to the orbital plane. So therefore, we expect that modeling this would improve spin measurements. And the reason why we are interested in improving spin measurements is because accurate determination of spin orientation can inform us about the formation mechanism by which the binary black holes were formed. We expect them to have or tend to have aligned spin if they were formed in the galactic field and they evolved as an isolated binary. On the other side, if they were formed dynamically in clusters, then we expect them to have a more isotropic spin distribution. So being able to measure this off-axis spin could inform us about the fraction of black holes that come from both of these channels. Another reason why this would be interesting is that, as I mentioned, that the out-of-plane kick is a consequence of this asymmetry. Therefore, for massive black hole mergers, if there are large enough kicks that could cause the black hole to be kicked out of the host galactic center, then that would change the, we assume that all of the galaxies have a central massive black hole, but if there are such galaxies where the central black hole has been kicked out, then that has implications on the massive binary black hole merger rates, which is also why this is an important thing to add. Now to the model, how exactly do we go about modeling it? So current phenom models, which are the frequency, state-of-the-art frequency domain models, they model the symmetric waveform, which is constructed from the 2,2 and the 2-2 for the dominant multipole. What we are doing is we are using this antisymmetric waveform, which is just the antisymmetric combination of the 2,2 and 2-2. And this is what our new asymmetry model would be. The reason why we do it this way instead of modeling the 2,2 and the 2-2 separately is because phenom models are very modular in nature, where you can keep adding new features and they are just sort of tacked on top of a baseline model. And doing it this way helps to preserve that modular nature of the phenom family of waveforms. So we make a model of the complex frequency series that this antisymmetric waveform is as an amplitude and a phase. And we do it in such a way so that we can simply construct the 2,2 and the 2-2 waveforms by combining the symmetric and the antisymmetric parts in the appropriate fashion. If you look at the plot on the right hand, I show the same plot that was there on the previous slide, but now I also show the symmetrized waveform. And this is the black dotted line. This is what is currently modeled in all phenom waveforms. So what I'll talk about next is the amplitude and the phase model separately. We know that in the inspiral region, post-Newtonian approximations are valid. And for the merger-ringdown region, we know that we have to resort to numerical relativity. Otherwise, the waveform starts to significantly vary. So what we have done over here is that we used of course, the antisymmetric terms or the mode asymmetries are already there in the PN terms. So we used a PN ratio of the symmetric and the antisymmetric amplitude for lower frequencies. And for higher frequencies, we use NR correction. So the main thing to look at over here is the red dotted line that you see on the plot is the PN ratio. If you just use the PN ratio, then as you can see that at about 0.01 or so, the PN ratio starts to deviate away from the NR data, which is the black dotted line. The NR data has some noise in the earlier frequencies, and that's why what we did was we constructed a couple of hybrids to figure out the appropriate minimum frequency at which we should look at our NR data and look at the modeling. Note that we did not use hybrids for the calibration. We used only the NR simulations for the calibration. For the lower frequency, we use the PN ratio. As I said before, the ratio is defined as the ratio of the antisymmetric amplitude to the symmetric amplitude. We note that the PN ratio is a function of the symmetric mass ratio, the spin magnitude of the spin, and also theta ls, which is the angle between the spin direction and the initial orbital angular momentum direction. And the NR ratio turns out to be this PN ratio times 1 plus V, which is the fit coefficient, times V to the power of 5, where V is just the frequency. Then we use the 80 simulations that Eleanor mentioned in her talk, the same 80 simulations, to fit B across the parameter space in mass ratio, spin magnitude, and spin orientation. And then this is the coefficient of correction to the PN ratio. We tune this to NR and produce surface fits of the B coefficients. And on the plot on the right-hand side, you can see that the model is shown in blue, which very well captures the PN part of the ratio and also estimates the NR part of the ratio very well. One thing that I haven't shown on this plot is that we expect the antisymmetric waveform and the symmetric waveform to fall off in the same way beyond ring down. Therefore, we clamp the ratio at the ring down frequency to be a fixed value beyond that point, which unfortunately I have not shown on this plot. Now to the phase model. For the phase model, from looking at the antisymmetric waveform in the time domain, we noticed that the phase of the antisymmetric waveform goes as the orbital phase plus the, sorry, there's a typo on the slide. It's phi orbital plus alpha, not phi orbital over 2 plus alpha. I confused that with phi GW. So in the inspiral part of the waveform, the phase behaves as phi orbital plus alpha. And therefore, we took inspiration from that and started looking at the phase derivative in the frequency domain. We looked at the phase derivative because the phase derivative has more features than the phase, so it's simpler to model that. And we noticed that the same behavior continues to prevail in the frequency domain as well, in the phase derivative. We noticed that at a certain transition frequency, the phase derivative transitions from phi orbital plus alpha to the gravitational wave phase, which is shown in the blue dotted line. Alpha over here is one of the precession angles that basically tracks the phase of the spin, or the rotation of the orbital angular momentum about the total angular momentum. So to model this, we use a tan H window to transition from region A to region B. The parameters of the tan H window is, of course, the transition frequency and also the width of the window. We calibrate both of these parameters to the NR simulations, treating them as free parameters and across the parameter space for all of those 80 simulations. And what we find is that a choice of 85% of the ring down frequency for the transition frequency and a width of about 0.005 was appropriate for all of the simulations across the parameter space. Therefore, we go back to using the same phase model across the parameter space without having to use additional fitting coefficients. Another nice feature of the antisymmetric phase being dependent on alpha is that we do not have to explore the extra dimension of NR simulations where we rotate the spins in the plane. So if you have a particular configuration where the spin in the plane is aligned with the separation vector of the binary, or if you have a configuration where it is at 90 degrees with the separation vector of the binary, we don't have to make separate NR, use separate NR simulations to calibrate that, because alpha already inherits this extra 90 degrees, and therefore we are able to just simulate in this particular direction where we only specify the in-plane spin, the in-plane spin component and not necessarily the angle. So now to talk about the model performance, I should say at the very beginning that while I am showing these as matches, but this should be taken with a grain of salt, because it is not meaningful to produce matches of just the antisymmetric waveform, which is what I've done over here, because a proper match for a waveform would be using the polarizations. The reason why we have done this is because we wanted some kind of a metric to estimate how accurately we have modeled this new quantity entirely. And the match seemed to be a good enough metric for that. These are not noise weighted, because that is not the purpose of these matches. This is just to look at how accurately these were modeled. This is testing the
Shrobana, you have 3 minutes. Sorry, you have 3 minutes. Thanks.
So we are testing the accuracy of the model against the calibration data set itself, because that is what we used to model this, and we just want to see how accurately we are being able to reproduce that. And the matches are of, like I said, just the antisymmetric waveform, which means the amplitude as well as the phase. And on the plot over here, I show all the 3 different components of it. So the green squares show the show how well the amplitude model was, how accurate the amplitude model is. So therefore, I use the model for the amplitude, but for the phase, I just use the NR data. And as you can see that it does pretty well for some cases, but then for some other cases, especially above case index 40 and up, it does it quite poorly, which ends up giving an average about a little above 10 to the power of -2. In the blue diamonds, I show the phase model performance, while for the amplitude, I use the data. And while the phase model doesn't go to as low values as the amplitude model, it does end up having more or less the same average, because it does better across the parameter space. And in red triangles, I show the full model, and the average of the matches end up being slightly above 0.98. Sorry, slightly below 0.98. So this is the first model of the mode asymmetries in the 2-2 mode, which is the dominant mode. This adds new physics to the frequency domain models that was not previously present in any of the other models, which would help us to measure KIG. None of the frequency domain models. The surrogate model has it, but not the EOB models. There is, of course, room for improvement. For instance, we haven't included any other asymmetries in the 2-1 or other modes. We also haven't tuned to full 2-spin parameter space. Both of these things are things we will look at in future, hopefully. This mode asymmetries model has been currently implemented in the XO4 model, which makes XO4 the only frequency domain model that would have mode asymmetries in it. But because of the modular nature, this can easily be ported into any frequency domain models, the existing ones or future models. We hope that parameter estimation with this model will improve our estimation of spins, particularly off-axis spins in binaries. And because in O4, we are expecting many hundreds of events. So we hope that will aid the extensive population studies and help us determine fractional binaries in different formation channels. Thank you for your time, and I'm happy to answer questions.
Thanks, Shrobana, for the talk. Let's see. Are there questions? Yes, Sebastian.
Hi, Shrobana. Thanks for a nice talk. I think it was on, could you go to slide 5, I think, where you had the PN ratio? This one here, so thanks. What's the motivation for v to the power 5?
Yeah. So this was actually tried with various different ones, and this was the one that empirically turned out to give the best fit.
Okay, thanks. And it's nice to see that you can just add one free parameter to this. Nice.
Any more questions to Shrobana? If not, let's thank Shrobana again for this very nice talk. And of course, if you have more questions, please reach out to her. Thanks a lot. Our next speaker is Avinash Tiwari.
Yep.
Hi, Avinash. So Avinash will be talking to, he will be telling us about probing globular clusters and other astrophysical environments with gravitational waves emitted by accelerated compact binaries. Avinash is from Ayuka, Pune. I think you can share your slides. Yes,
Okay, so
I think
should I start?
Avinash, yes, you can start. I will remind you after 12 minutes. Your talk is for 15 minutes plus 5 minutes question and answers. And all those who have questions, please post them in Q&A box so that we can communicate that to Avinash towards end of his talk. All right, Avinash, you can get started.
Okay. Hello, everyone. So I'm Avinash Tiwari, and I will be talking about probing global clusters and other astrophysical environments with GWs that are emitted by accelerated CBC mergers. So we know that till now around of the order of 100 GW events have been detected by the LDK collaboration, and all of them, in fact, most of them are coming from binary black hole mergers. Couple of them are BNSS, and couple of them are NSBH events. And so it is well known that a binary left on its own will not evolve and merge within the Hubble time if the energy, it is losing the energy only through the gravitational waves. So how do these binaries that have been observed by GW detectors are forming is still an open question. And to answer this, a number of formation channels have been proposed. Most of them are broadly in two categories. First is isolated evolution. The other one is dynamical evolution. In isolated evolution, the binaries mainly form through chemically homogeneous evolution or through common envelope or stable mass transfer, while dynamical evolutions comprises of the models that predict these mergers to be happening in globular clusters or nuclear star clusters or any dense stellar environments, basically. So we asked that, so it has been basically suggested by study done by Jevin and et al. That any single one of these models explaining all of these mergers is strongly being disfavored, such that if you consider 4 of these formation channels, and then the probability that every one of these 4 is explaining at least 10% of the observations, that probability comes out to be 79%. So it is still an open question: how do we disentangle the formation channels? And so we ask a question: does there exist any potential signatures or smoking guns in the GW waveform itself, which can tell us about the formation channels? So one such signal could be the acceleration of the binary center of mass of the binary. This is basically because even if you consider isolated evolution case, in which case even the galactic potential is there, or in dense stellar environments, the environments potential is there, or in encounter mergers or third body in the vicinity is there. So accelerations could be one such signature that can enable us to know the information about the formation channels. So why acceleration? So the point that, for example, if there is a constant velocity, then the Doppler shift will be degenerate with this source frame mass, and we cannot remove this degeneracy. While if there is a line of sight acceleration, then in that case, the extra redshift will be dependent on the time, and hence we will be able to break this degeneracy, and this will modulate the GW waveform. So if you consider the stationary phase approximation, then under that approximation, the GW waveform is given by this expression, where m is the Chern mass, dl is luminosity distance, f is frequency of the gravitational waves, and psi is the unperturbed phase, which is a polynomial in B, where we are defining using this expression, and m is the total mass of the system. And the phase correction is given by this expression, which is a -4 pn leading order correction in phase. And since this is a negative pn order correction, it generally doesn't have any counterpart in usual GW waveform analysis, except when if you consider the variation of G or acceleration, accelerated expansion of the universe, but those happen at a much larger time scales than this motion of the center of mass of the binary. And also this -4 pn means that the best constant that we will be getting will be from the low mass binaries and low frequency bands. So we did the parameter estimation for this acceleration on GW1708, 17, 19, 04 to 5, and we find that in both of these cases, the acceleration is consistent with 0. And based on this 95 confidence interval, we can put a constraint on the distance of these mergers from a supermassive black hole. And then we find that since GW1708 had an electromagnetic counterpart, and which means we know its host galaxy, then we know the mass of the supermassive black hole. So we get that it should have merged at least 12.1 astronomical units away, astronomical units distance away from the SMBS, which is the case as we know that from the EM observations that it merged at roughly at 1.9 kiloparsec, if I'm right. And for 1904 to 5, we do not have any such counterparts. Then we put a mass dependent constraint that if suppose there is a 10^8 solar mass supermassive black hole in the vicinity, then this would have merged at least 7.2 parsecs away, astronomicals away from the galactic center. We also put the constraints on the measurement of the acceleration for LIGO at a plus sensitivity and the Einstein telescope. So for this, we use the Fisher matrix analysis, and we find that the best constraints on these plots are at a fixed SNR of 10. Then we find that the best constraints in O5 are coming are of the order of 10⁻⁶, while the worst constraints are of the order of 10⁻�3. While in case of Einstein telescope, since they can probe much lower frequencies, so this is why the best constraint is of the order of 10⁻⁹, while the worst constraint is of the order of 10⁻⁸ per second. We also did the similar analysis for DESIGO and LISA. Then we find that for at SNR 10 in DESIGO, the best constraint is of the order of 10⁻⁻16, while the worst is of the order of 10⁻⁻10. And for similar cases with LISA also, that the best constraint is of the order of 10⁻⁻16, while the worst is of the order of 10⁻⁻14, which is for the binaries as much as 2000 solar mass. And so this is just because of the fact that these detectors probe much lower frequencies than the 3G or LIGO detectors. So then we did a study of how much acceleration there is these binaries have in Milky Way like galaxy, and if we can probe these or not. So since in DESIGO the SNRs generally are typically higher, so we have the studded region which is at SNR 1000, and we find that the best constraints for the DESIGO basically can probe as far as a few kiloparsecs away from the galactic center, and while the third generation detectors can probe most of the inner parts of the these galaxies. And so then we did our study on these accelerated BBHs in globular clusters. And so for this, we have used the cluster Monte Carlo simulation of global cluster, which was performed by Kramer et al. And from there, we make a fiducial catalog of these BBHs that merge well within the Hubble time, and then we extract the information about these mergers. Just like we need their merger time. From this merger time, we consider the evolution of the global clusters, and then we get the enclosed mass within the merger radius. From there, we can calculate the acceleration as it will be just gm by r square basically. And then we randomly draw 5000 redshift from Maddow-Dickinson distribution. So Maddow-Dickinson distribution is an it's basically we consider it from 0 to 10 only, because it's from the observations, and the observations are up to redshift 10, so we haven't gone beyond that. And so this is this basically it's coming from the this takes into account the star formation history basically. And then we calculate the merger redshift, considering that the binaries will take a time to evolve. So from there, then we get the luminosity distance and calculate SNR. We find that this SNR in LISA or DESIGO is basically in DESIGO, if it is greater than 10, or in LISA it is greater than 8, then we consider the sample, or else we reject the sample. And then we perform the Fisher matrix analysis to get the RMS errors of the measurements. And suppose if we are finding that the acceleration that we are getting in these for these mergers, if it is greater than the error that we are getting, in that case we will be able to constrain the acceleration from these detectors, and we denote them as found mergers. And if we are the acceleration is smaller than the error, which means this won't be constrained from these the acceleration won't be constrained from the detectors, and we denote them as a missed mergers. Then we plot the histograms of these found and missed accelerations. So for this histogram, we have considered the metallicity weight, detectability weight, and the initial cluster mass weight. And we so the left plot shows the results for Desigo, while the right plot shows the results for Lisa. So green ones are here the missed ones, and the orange ones are found ones, and blue ones are the all of these mergers that we have considered. So we see that the with Desigo there will be of the order of 12% of these mergers that will have a detectable acceleration, while in Lisa the same number is of the order of 14%. And we also see that in Desigo, the peak of this acceleration is of that will be detectable is of the order of 10⁻⁻15 per second, while in case of Lisa, this peak is at the similar location. But we notice one thing, that in Desigo, the accelerations as high as of the order of 10⁻18 are detectable, while in case of Lisa, this is not the case, because here there's a cutoff which is at 10⁻⁻16. So this we are observing basically due to the fact that in Lisa the SNRs are basically smaller, which means the only much higher accelerations will be detectable in Lisa. And also we also studied the effect of the metallicity on the distribution of these found mergers in Desigo and Lisa. The left one shows the distribution for different metallicities in case of Desigo, and while right one shows the same for Lisa. So in both of these, we see that the most contribution which is coming to the found mergers is coming from the moderate metallicity. This is due to the fact that the redshift, so this Maddow-Dickinson basically peaks around 2, and at that redshift, the metallicity weight of these clusters basically having a metallicity of 0.002 dominates. And we also see a systematic shift towards the rightwards when we are decreasing these metallicities. So this is due to the fact that low metallicity clusters are the massive clusters or old clusters, and they have these mergers which are much massive. And since this correction that we have is a -4 pm order correction, which means that higher masses will have a weaker constraints on the acceleration. And this is why they need to have a higher acceleration so that they will be detectable by these detectors. This is why we see a shift in these distributions. We further then study the effect of the metallicity and the virial radius in case of Desigo on these on the redshift distribution is the merger redshift. So again, here we see that most contribution is from the similar I mean the moderate ones, while there is a systematic shift to the rightwards in the merger redshift also. This is due to the fact that the low metallicity clusters generally have higher mass BBHs, that is massive BBHs, which will take smaller time to evolve and merge. And this is why in case of this 0.0002, even we can see these mergers and consider the accelerations at redshifts higher than 8 or 9, while in case of the higher metallicity this is not the case. This because they will have a smaller mass binaries and it will take much longer to evolve and merge, so they will be detectable at lower redshifts. We also see that so here a small RV basically means that the globular cluster that we are considering is denser. So we again see that the denser clusters have the most contribution. This is to the found accelerations. This is due to the fact that the denser clusters will mean that
Avinash,
the
you have 3 minutes.
okay. So, we see that these high, denser clusters will have a larger systematically larger accelerations, and a large number of them will be detectable. And also we see that there is a constant shift towards leftwards with varying increasing RB, which is puffier clusters will have the mergers at a lower redshift. This is again due to the fact that in lower mergers the accelerations will be smaller, and then we will be able to constrain these accelerations only when they have a high SNR, and this is why we need them at a lower luminosity, much smaller luminosity distance. So this is why a systematic shift towards leftwards. So in case of LISA, we don't see any such. So the fractions are similar in case of LISA, that the most contribution is from the denser clusters, but there is no shift as such in case of LISA. This is I haven't presented the results for LISA here basically. So this is also because in case of LISA, if you see that the horizon redshift for these stellar mass binaries is of the order of, I think, around 0.3 or 0.4 or so. So in that case, so we won't see any difference between these distributions basically. So, and to summarize this in brief, we see that the measurements of acceleration yield 0 acceleration for 17 with 17 and 19 or 4 to 5, and at a center of 10, the best constraints in O5 are of the order of 10 power minus 6, while in Einstein telescope these are of the order of 10 power minus 9. Same in Desigo is of the order of 10 power minus 16, while the worst in Desigo was of the order of 10 power minus 10 per second. And so one thing to note that I want to mention here is that for LISA and Desigo, I have considered 4 years of the observation time. And with third generation detectors, we see that we will be able to probe the inner parts of the galaxy for line of sight acceleration, while Desigo will allow us to probe in fact, most parts of the galaxy. And in fact, when we go to global clusters, we see that roughly of the order of 12% of the beaches that formed in global clusters will be detectable, while the same number for LISA is around 40%. And also the most contribution to the found mergers is coming from moderate metallicity and denser clusters, basically. Thank you for listening.
Thank you, Avinash. Thank you for the nice talk. Questions for Avinash? John? Yeah, you can.
Hi, Avinash.
Yeah.
Thank you for your talk. Please, I'm doing theory, so may I ask you, where is planned the Desigo project? When it will be launched? Do you know yeah? So
okay, so I'm still not sure about what is the plan for the launch of Desigo.
Thank you.
Avinash, I have a question about your population. So you have taken, did you take a very specific population for the from which you considered the acceleration? Is there any prior which you took on the acceleration for your study?
No. I didn't require the prior. It's just because, for example, we directly get the information about the acceleration from the simulations, and then we perform the Fisher matrix because we know these luminosity distances and the detector frame masses. So then we are just comparing those two numbers. That if
I see. Okay, I understand. Yeah, but then for the simulation, did you consider? What population you took for the PBH? So I think I did not understand that part. for your entire study, I mean, what is the
they have-
distributions which you have considered? Yeah.
Okay, so I think you are do you want to know about the masses of these
Yeah,
devices? Is it? So these are stellar I mean binaries that they have considered in these simulations, and for this they I think consider Krupa IMF for this in the primary merger and sorry, a primary black hole, and for the secondary they consider uniform distribution in mass ratio basically.
Okay, fine. All right. Okay, thanks a lot. Any further questions for Avinash? Okay, if not, thanks a lot, Avinash. I'm sure if there are any questions, people will try to reach out to you. Now
sure.
let's take another break of 10 minutes and then we will reconvene after 10 minutes. Hello, everybody. Let's resume our session. So our next speaker is, let me just check, Maria de Luplanas Lompard. Maria, I'm not very sure whether I pronounced your name correctly.
No,
yeah, so she'll be talking about exploring the remnant properties of processing black hole binaries by combining numerical relativity and extreme mass ratio data sets. Thanks a lot. I think she has already shared her talk.
Yeah, you can
So
see.
off to you, Maria. Maria, I will give you a reminder after 12 minutes. Your talk is for 15 minutes, and I request everybody to place Q&A questions in the Q&A box so that we can look at them towards the end of her talk. All right, Maria, you can begin.
Okay, thank you so much. Hi, everyone. I'm Yuk Planas, and I will be talking about the remnant properties of processing black hole binaries by combining numerical relativity information and extreme mass ratio datasets. So, first of all, black hole binaries have been the most detected source of gravitational waves so far, and the modeling parameter space, if we assume circular orbits, spans 7 dimensions, which are the 2 black hole spin and then the mass ratio. And in order to cover this huge parameter space, we need to combine different sources of information, such as NR, and what we will do here is to include information from the extreme mass ratio limit. This has already been done for the aligned case, where only 3 dimensions are needed, and we want to extrapolate that and use it for the 7-dimensional space. So first of all, as a brief reminder, because some people before have talked about it, I will talk about aligned and precessing systems. Depending on the orientation of the spins with respect to the orbital angular momentum, we can differentiate 2 cases. In the case in which the spins are aligned or anti-aligned with the orbital angular momentum, there's a symmetry between the with respect to the orbital plane, which is preserved during the whole evolution, and then only 3 quantities are needed to describe these systems, which are the 2 spin components aligned with the orbital angular momentum and the mass ratio. And only 2 timescales affect this problem, which are the orbital one, which is the fastest, and then the radial one. However, in the more general case where the spins are not aligned with the orbital angular momentum, then these symmetries are broken and both the spins and the orbital angular momentum show a precessing motion, which is also translated into the wave, as you can see in this plot here, as some oscillations. Then in this case, we need the 7 dimensions to characterize the system, and a new timescale, the precessing one, is included to the previous one, so the orbital and the radial. However, the orbital one is still the fastest, so the emission of gravitational waves is mostly due to this, and this is something that we will use afterwards. So we have characterized precessing systems, and we have seen that there are 2 particular difficulties that we need to deal with, which are the huge parameter space, so we need to deal with 7 dimensions, and then there are no symmetries that we can use to simplify these problems.
In our case, to cover the parameter space, we combine different sources of information. We use 3 different NR catalogs. So we have here a plot where we show 3 dimensions, the eta dimension, the spin of the largest black hole, and of the secondary object. And we have the SXS data that covers mostly the comparable mass regime up to Q4, Q6 in some cases. They are quite distributed across this region. Then we also use the BAM catalog, which Eleanor presented a few talks before, which are these blue points here in the chi2 = 0 plane, that they are evenly distributed in the parameter space. And then we also use some few Einstein toolkit simulations run in our group, which are these green points around that are for high mass ratios, which go up to Q18. But we just have a few of them, so they are not. They are still not covering the full region that we are missing here. In order to add more information to ignore the fact that here we don't have data, are these points here, these orange points here that are extreme mass ratio waveforms that are from this reference here, and they are at Q1000 and are single spin too. So once we have our data set, we want to, well, first, we used more data from the surrogate here to cover this region in more detail because it has been calibrated up to Q4, and that's where we also use it to have more data. And in order to put all these data set in a consistent way, we need to deal with the fact that we don't have symmetry. So in this case, since both the individual spins and the orbital angular momentum show a precessing motion, there's no natural inertial frame. So what we do is to define a reference frame at some reference time that we chose it to be 100 M before merger, and we point the orbital angular momentum along the z-axis, and then we define the x-axis from the smallest to the largest black hole. This way we can put all this data into this inertial frame and we can perform our comparisons. However, for the extreme mass ratio limit, we need to do a bit more work. As I said before, we rely on these on the data set which are from these 2 references, and we have around 6,000 waveforms which vary in the spin of the largest black hole, and then the inclination angle and the angle of the final plunge. And we get the trajectories, the constants of motions, and the waveforms. And the first step is to translate it into this new parametrization that I presented before. So with all the trajectories, we first performed this rotation. And once we have the data in this new inertial frame, we compute the remnant quantities from both the data that we have, and we also use the precessing geodesic equations at the ISCO. And what we saw here in this plot, you can see the difference between the remnant properties computed from the data and the geodesics, is that the errors that we get are so small that within the accuracy that we want in our model, we can also use geodesics in order to get more data close to the extreme mass ratio limit. So once we have a consistent data set, we can use it to calibrate precessing models. So due to the current data limitation, models that are NR informed are constrained in terms of the mass ratio. So for instance, we have the model presented before and also the surrogate. And here I should mention that a week and a half ago, there was this new model which actually uses kind of the same thing that I'm presenting here in order to extrapolate the surrogate model up to extreme mass ratio limits. But this is not included in the current results, but I will update it for the publication that I'm preparing. So our idea is to combine all the NR information and also analytical information to get in concrete a remnant model, which currently works for the single spin case across all mass ratios. And although it has been calibrated up to a spin of the largest black hole equals 0.8, it actually extrapolates well up to extreme spins. And we will use hierarchical methods. So the first step is to think about what's the best quantity to fit for each remnant property. For the final mass, I said before that the precessing times scale is much lower than the orbital one. So the orbital one is the one that dominates for the emission of gravitational waves. So it makes sense to fit the difference between the precessing and radiated energy and the aligned energy that we would get in that system. So this is the quantity that we will fit, which actually in current phenomenological models is neglected. And then we can compute the final mass. For the final spin magnitude, we can assume a correction to, for instance, what has been explained in this paper here, but it's used in phenomenological models, which consists in assuming that we have a contribution from the aligned part, where we can use the fit, which is already used for aligned spin systems. And then we use the in-plane component of the spin, which in this case is just for one because we are in the single spin case. And we assume that it's constant throughout the evolution, which is also a good approximation, which is being used right now. And here it's why we include a new correction, which is the quantity that we want to fit. And it turns out that for this correction here, we can get this analytical expression for the extreme mass ratio limit. For the high mass ratios, very high mass ratios, the dominant term is the linear one, and we can see this oscillatory behavior in terms of the inclination angle, which comes from this cosinus. And then we have a quadratic term, which is usually neglected in the extreme mass ratio expansions. But it turns out that if we go up to the comparable mass regime solving geodesic equations, this term gets dominant, and we get a different shape, which doesn't show the oscillations that we were seeing here. But this is actually the behavior that we see in our data. So these points here are the numerical data, and it's delta squared computed from our numerical data. And we see that the behavior is the same. So what we get is that the extreme mass ratio limit is giving us some intuition on how to reach the proper limit, but also how this behaves across the full parameter space, even for the comparable mass regime. So once said that, we can go and proceed to fit the quantity across the full parameter space. Since we only care about the single spin, we have 4 dimensions, but the in-plane orientation of the spin doesn't matter in this case. So we just have 3 dimensions, but we still have to split it. So we first show our data in plots showing the evolution of the spin magnitude eta at fixed thetas. We do it for all these thetas. Once we have this for 5 thetas fixed, here I'm showing just one, we then connect the extreme mass ratio limit, where we use Embry data and also geodesics with the comparable mass regime in a smooth way. And once we have that, we can fit for each of these 5 surfaces these ansatz, and we will get coefficients that depend on the fixed value of theta. And once we have that, we then fit each coefficient in terms of theta. And what we found here, which is also something that we could expect from the previous slide, is that the appearance of these coefficients is actually the same that we saw for Q fixed and theta evolving in the extreme mass ratio limit, which is also a very interesting result by itself. And once we get that, we can include the coefficients into our fit, and we get a final fit which works for any theta, chi1, and eta. And we can now check the accuracy of the final spin model here. And here we are comparing with the surrogate up to Q6. And this is where I will update my results, because then I can evaluate the whole data for all the models, because the new surrogate goes up to Q extreme mass ratio. So what we see is that our model reaches same accuracy as the surrogate model and increases 1 order of magnitude the one that we had before, which ignores the delta squared correction, which is the quantity that we have fitted. And even if it achieves the same order of magnitude, it is much faster, which is very important for waveform modeling efforts. So while we can now proceed in the same way for the final mass, fitting the difference between the precessing energy and the aligned energy. And since this is a very small quantity, we know—
Maria, you have 3 minutes.
Okay, great, thanks. So we saw that since it is a very small quantity, we first needed to improve our current model of the aligned spin energy. And we did it, and you can see here the new energy with respect to the O1 in green. And here is the difference, the plot of the difference. And this is because it was not capturing well the extreme spin, extreme mass ratio limit. So once this is fixed, we proceed in the same way. We compute the delta E for our whole data set and show it in terms of fixed theta. We then connect the comparable mass regime with the extreme mass ratio limit and fit each of these surfaces using these ansatz. And we then fit each coefficient in terms of theta. And we can now get a final fit, which works for any chi1, eta, and theta. And we check the accuracy of our model, and we get similar results than the ones that I showed before. Same accuracy as the surrogate, order of magnitude, but much faster, and improving our previous model, which assumed that the precessing energy was the same as the aligned one. So now moving to the conclusions, we have seen that due to the high dimensionality of precessing systems, and our informed models are very challenging, we don't have enough simulations to cover the 7-dimensional space, and high mass ratio simulations are very expensive, and we don't have enough in our information for Q higher than 19. So we need, and that's what we did, to use the extreme mass ratio limit to reduce the number of simulations that we need. We then created a consistent data set combining NR waveforms, the surrogate waveforms, and the extreme mass ratio limit, and generated fits for the remnant properties, which outperform the previous phenom models and are faster than the surrogate ones. And what we saw is that the final spin morphology is actually quite similar to the one that we would expect for the Emery limit, even at the comparable mass regime, and that we cannot neglect the quadratic term, even though that's what in most cases we do, because it doesn't contribute, but in this case it does. And having a good model for the remnant quantities, it's essential to characterize the waveform ringdown, which is important for test of GR and also for modeling purposes. And finally, even though we have focused on the single spin limit, that's the baseline for the double spin case, because when we want to reach the extreme mass ratio limit, the double spin is a very small correction, which might not be even important for our purposes right now. And we are currently working in including the double spin case for the comparable mass regime. So that's it, and thank you so much. And now I'm happy to take any questions.
Thank you so much, Maria, for such a nice talk. Yes, there is a question. Sebastian?
Hi, yeah, thanks. That was a really, really nice talk.
Hi.
I had a question, I think, on slide 8.
Yep.
Yeah, here. On it's okay. On point 4, where you have your ansatz and you have all those different powers of eta and chi, how did you come to this set of combination?
Yeah, so well, first was a bit of visual inspection, and once we had that, I was trying, like, in a recursive way, first fitting like all the terms that I might need in order to get up to the power that I wanted for both eta and chi1. And once I got that, I was checking, since I just have 5 cases, I could go in detail in each case. And I was checking those parameters where the value of the fit that I was getting was not 0 or close to 0, or could be 0 in the range of the parameter. So I was getting also estimates for the higher and lower bounds. So I could remove those that were close to 0. And then I was also getting checking the error and comparing those where the error was lower. So in the end, these were the terms that worked better for all the cases. So this way I could go and fit each parameter afterwards across theta, sorry. So
great, thanks so much, that makes sense.
Okay, thank you.
Maria, I have one curious question. So this you've done it for single spin, right?
Yeah.
So what are the sort of, when you go next to include both the spins, what are the difficulties? Or yeah, I mean, I'm just curious. Yeah.
Yeah, sure. So actually this is what I'm working right now. well, the main problem is that we include 2 more dimensions because we will need both the magnitude of the secondary spin and the orientation with respect to L of the secondary spin. So this difficults a lot the fitting procedure. And that's mostly the main difficulty. So what I'm trying to do, since when we reach the limit, the extreme mass ratio limit, the secondary spin is a very small contribution, we could ignore that. What I'm trying to do is to find a parametrization which for the comparable mass regime takes into account both spins, but then when moving close to the extreme mass ratio limit, it like kind of tends to the largest spin. So what I'm trying to get is the best parametrization that combine information for both spins in close to the comparable mass regime and transitions into the single spin case for larger mass ratios.
Sure. Yeah. Thanks a lot. Thanks a lot for the nice talk. I think you can stop sharing.
Yeah.
All right. Thanks. Yeah. Our last speaker for today's session is Peter James Lee. Peter is from Albert Einstein Institute, Potsdam, and he's going to tell us about the title is To Ring or Not to Ring, the Tale of Black Hole Quasi-Normal Modes. Off to you, Peter. Peter, I'll give you a reminder after 12 minutes. Your talk is for 15 minutes and then 5 minutes of Q&A. You can start.
Great, thank you. Hi, everyone. Thanks for attending my talk. Today, I'm going to be talking about black hole ringdowns and how we can best understand overtone extraction and fitting and what our fits are actually doing physically. And so this is based off of work that has been recently accepted for publication in PRD, performed by myself, Sebastian Volkel, and my PhD supervisor, Harold Pfeiffer. So a little bit of background that's probably wasted on everybody here, but when we consider binary black hole systems, and the broad definition of what a ring down is that once the 2 black holes have coalesced, one is left with just a remnant perturbed Kerr black hole. And this Kerr black hole will settle down into its stationary state. And as it does so, it's going to emit gravitational wave radiation. What quasi-normal modes are, or QNMs, are complex numbers that encapsulate the frequency of this kind of settling or ringing and the decay rate. And a byproduct of the No-Hair theorem is that the QNMs for this radiation is entirely determined by the spin and the mass of the remnant black hole. And so just to make sure everyone's on the same page, I'm going to talk about a fundamental mode. This is in a ring down the longest live mode, so this lowest decay rate, and then higher order overtones, the first, the second, the third, are increasing decay rate. And so the motivation for this work is that the overtone structure of a ring down and its extraction is a really important test for GR. Already in LIGO waveforms, we can see the fundamental mode. The extraction of the first overtone is something that's debated, but if we can look for possible deviations from GR and the overtone structure, this will be a very useful tool for testing general relativity. And overtone extraction forms the basis for black hole spectroscopy. Now, in the last few years, there have been several new findings regarding both the robustness of how we can extract first order overtones from simulations, and also the presence of nonlinear second order QNMs. So when you compute what a QNM is, you do it in the linear perturbation theory, but one could also look at second order perturbations. And so I have 2 plots here on the bottom. The left one shows the improvement in our fits when we include one of these second order QNMs, while on the right side, we see the improvement in our fits as we include more and more overtones. So even if we can't see higher order overtones yet, in next generation detectors like LISA, where we'll have much higher SNRs, we hope that we might be able to extract overtones, and we need to prepare to know what does it mean to extract an overtone. So we want to keep things simple so that we can really focus on just the most basic pitfalls we might fall into. So we're going to generate waveforms by considering the wave equation for a scalar field in a Schwarzschild spacetime. Now, with a little bit of work, one can massage this equation into the form of the top equation here, which is a 1+1 wave equation with the potential, the Reggie-Wheeler potential, or I'll refer to it as the GR potential, being the third line here. Now, when one does time domain evolutions of this equation to generate waveforms, one can find that analysis can be made tricky by late time tail effects. So this is a power law tails that decay like some inverse polynomial and eventually become dominant in your signal. They become larger than the exponentially decaying QNMs. To kind of mitigate this, one could consider other simpler potentials. And one of interest in the last 20, 30 years was the Puschel-Teller potential, which is the bottom one here. The way this works is one can pick the values V0, alpha, and X0, so that the peak of this potential is in the same location as the Reggie-Wheeler potential, has the same amplitude, and the second derivative at the peak agrees. And when one does this, first, you have no tail effects in your ring down, but secondly, your fundamental mode is very, very close, not exactly the same, but very close to the fundamental mode for GR. And the overtones imaginary parts, so the decay rates agree to about percent level, but the frequencies are very different. So to generate these waveforms, we do time domain evolutions using finite differencing and stencils that are centered in time and space. Our initial data consists of incoming Gaussian wave packets. So in the top right here, you can see those Gaussian wave packets coming in for both of our potentials, scattering off of the potential. So this is two separate evolutions, and then the waveforms traveling out. And so we can observe this waveform at some faraway extraction radius, which is the bottom plot here. Now, when doing these ring down fits, an issue you very quickly run into is you have to decide how much of the waveform you want to use. If you go too late, your waveform may be dominated by tail effects if you're using the GR potential. And if you go too early, you might be including the initial prompt response where your initial data is kind of interacting with the gravitational wave. If you're not in a linear case, so you're looking at, say, NR waveforms, you may start to see nonlinear effects, which you can't capture with QNMs, or maybe you are going so far back that you now have two black holes instead of one, and so your approximation doesn't make much sense. The way to get around this typically is to repeat all your fits for using different amounts of the waveforms, compare and contrast them and see how it works. So this blue shaded region is a typical fitting regime, or a typical fitting region we use. Now, I've been talking a lot about doing fits. What fits are we going to do? So we have two different types of fitting, and for all of these types, you can choose how many modes you want to fit. So whether it's just the fundamental mode, include an overtone, etc. The first type is an agnostic fit. This is where for each mode, one fits for an amplitude, a decay rate, a frequency, and a phase separately. So each mode comes with 4 parameters. This is maybe the kind of brute force approach, where if you can find quasi-normal modes and overtones by doing these types of fits, you can be very, very confident that you have found them in the signal. However, the amount of parameters grows quite quickly, and so these fits are not always the most stable. To kind of help our fits converge, we can do a theory-specific fit. This is where we fit for the amplitudes and the phases the same, but we now assume that all frequencies and decay rates depend on just the mass, since we're working in spherical symmetry. And so now you get an extra amplitude and phase with each mode, but you only have one mass parameter for each mode. And maybe the kind of unique part of this work is when we take, say, a Puschel-Teller waveform, we actually have 2 options for theory-specific QNM spectrums to use. We could either try using the Puschel-Teller spectrum, which is the one that we would expect to see in the signal, or we could try fitting it using the GR spectrum. And what this means is that we're fitting with a fundamental mode that is pretty correct, but the overtones are wrong. And so we can try to compare and contrast how these fits perform to try to work out what are good diagnostics for overtone extraction. So the first and obvious thing to look at, typically for these fits, are the recovered mismatches in mass. So the x-axis here is the starting time of our fit. So that determines how much of the waveform we're going to use. While the y-axis are the mismatch and the error on the mass extracted respectively. So for when we're fitting a Puschel-Teller waveform and we're using the Puschel-Teller spectrum, everything looks as you would expect. As you include more overtones, more fitting functions, your fits perform better. This isn't enough to say that you have found an overtone, because you could just be fitting away any other contribution to the signal that lets you get the fundamental mode better. But you can't say that either. It could be that you are capturing an overtone. So what happens when we try to apply the wrong spectrum of overtones to this signal? And this is maybe non-trivial. We see that at early times, when we expect the overtones to be most important, the fits behave really similarly. And the main dependent thing is not the number, or not the correctness of the overtones, but the number that you use. At late times, you can see if you're using the right model, but this is perhaps what we believe this is due to is the fact that the fundamental mode is close, but not exactly right. We could also do some agnostic fits. This is a good sanity check, and the fundamental mode agrees with the theory specific for one for Puschel-Teller. When you add an overtone, it seems to outperform both models. This is probably due to the fact that it can capture both the overtone, but also maybe some other non-QNM effects in the signal. We can play the same game for a GR waveform. And so here we see that the structure is qualitatively the same as for the Puschel-Teller system. Maybe the interesting feature is at the end, our analysis is limited because of these power law tails that I was talking about earlier. But I would say here it's even harder to distinguish whether one is using the correct spectrum, the GR one, or the incorrect one, the Puschel-Teller, at least until very, very late times. So I'm going to focus on just analyzing a Puschel-Teller waveform for the rest of this talk. I have some plots at the end if you're interested in seeing how it translates for GR, but most of it is the same, albeit just a little messier. So the kind of next obvious thing to look at is the actual QNMs that you are extracting. So here, different symbols indicate different types of fits. In these plots, I'm only ever fitting for the fundamental mode, no overtones. Triangles is the agnostic fit, squares are the correct Puschel-Teller spectrum, and circle is the incorrect GR spectrum. And when you're just fitting for one mode, everything works pretty well. The fundamental mode doesn't disagree so much, so it all works nicely. When we now include an overtone, things are maybe a little messier, but at least in the Puschel-Teller case, we can still largely extract the first overtone. If we now look at n equals 3, so we're fitting for 2 overtones, we kind of start to see a trend that because all of the overtones depend on one parameter, namely the mass, the fundamental mode for the incorrect fit, so the circles, is trying to kind of overcorrect to get closer and closer to the square. And you can see this by, in the overtones, the kind of final convergent places is offset from the analytic value, which is the larger circle. Now, the last thing we could do when analyzing these fits is look at the excitation coefficients. These are the amplitudes that I pointed out at the beginning. And what these are is, these are determined entirely by the type of perturbation that you do to the remnant black hole. They're not known analytically, so it's something you have to fit for. If we were to consider the excitation coefficient at the peak of the signal, this value should be independent of how much of the waveform we use. So we would expect it to be constant in these plots. And so this can be a nice way of trying to gain insight into whether we are actually fitting QNMs or just fitting something else in the signal. For the fundamental mode, we see that we recover it pretty well. As you include more overtones, you can get it earlier and earlier. And because the fundamental mode agrees pretty closely between these two models, you can fit it no matter what. However, in the overtone, so we're looking at the bottom plot here, at early times, we see that all the fits behave pretty similarly and kind of tend to some constant. However, at around T0 minus T peak equals 30 or 40, the incorrect GR fit diverges. And this is maybe a good sign that we are using the incorrect model and this is the right way of looking at it. Perhaps the issue with this is when you're applying this to actual data, we're not always going to have the ring down available at such late times because of noise eventually becoming dominant. And so we may only have access to the early part. And if you only have access to, say, from 0 to 30, you can't really differentiate these fits. Putting this all together.
Peter, you had
Yeah.
3 minutes. Thanks.
Okay, I'm coming to the end anyway. Putting this all together, if we consider just the mass and mismatch plots, we see that the quality of our fits is largely just dependent on the number of overtones we're fitting for as opposed to the correctness of those overtones. So this is not a good way of determining whether you have extracted an overtone. The excitation coefficients make the picture a little more clear. However, if we were to limit ourselves to only looking at early times, which is maybe the case when looking at actual data, this is where the models all behave most similarly. Overall, this can make it very difficult to quantify whether one has physically extracted an overtone, however you may want to define that, or whether you're just fitting away other non-QNM contributions, be they nonlinear effects, tail effects, what have you. So to wrap it up, in this work, we generated linear waveforms using several different types of wave equations and analyzed them using a variety of different fitting models. We found that the mass inferred from each of these fits depended mostly on just having the fundamental mode correct and the number of overtones you included, as opposed to the correctness of those overtones. The next steps would be to try to apply this type of procedure to full NR waveforms for binary black hole system, so that we can further explore different types of overtone structures and different types of ring downs. But ultimately, what we really need to do is to better define what it means for an overtone to be extracted or physically present in a ring down signal. Thank you all for listening, and I look forward to your questions.
Thank you very much, Peter, for such a nice talk. Questions for Peter? It looks like I think everybody is tired. Yeah, it was a long session. Yeah, thanks a lot for your talk. Yeah, I'm sure, I think you might get questions. Is this is this paper already published, or is it something which is going to be
it's being accepted for accepted for publication, but the archive link is here.
Okay, all right. Yeah. So I'm sure I think you'll get more more questions very soon. Yeah. All right, then. Thanks to all the speakers who presented their work in this session, and thanks for all the participants who were part of this session. I think with this, I close this session. Good day.